I hope it's recording. It looks like it is on
I
Zoom.
heard the recording button.
Great. Okay, well, welcome. My name is Sai. I am I'm going to be a second year graduate student in the fall. I have a couple people in person here. Good to see. I see we have quite a few people in the Zoom call as well. Thank you for coming. Welcome. So like I said earlier, this first week is going to be sort of standard stuff in homological algebra. I want to avoid saying anything too profound. You'll find that a lot of the things that we talk about are, I don't want to say straightforward, but if I say something and you don't believe it, you should prove it. And you can't. Follow your nose. A lot of this stuff is like this. It can be very tedious, though, to actually check all of these things. So often people don't, which is fine. I mean, don't worry about it. But a lot of these things are like believable and things we'd hope to be true. And you'll see. Okay. So where to begin? So maybe for 2 seconds, I should just say why we care about homological algebra. Mostly, we like to do useful calculations, and homological algebra is like a useful tool for carrying out these calculations, for answering questions in algebra, algebraic geometry, topology, number theory, whatever you can think of. Homological algebra is it's a very useful tool. Okay. So to start, today is mostly going to be language. I want to start by talking about additive categories. Additive categories. So we say that a category A is additive if, so there are like 3 or 4 things that we want. So for any 2 objects, x and y, xy has the structure of an abelian group, or we can give it an abelian group structure. Can be given the structure of an abelian group. What do we call this? An AB enriched category? I don't know. Whatever.
Yes, that's what you call it.
Awesome. Great. And moreover, so we can compose morphisms, right? And we want the composition should be bilinear across this abelian group structure. So composition for any 3 objects, I should say. So hom yz times, so you take any 2 maps that you want to do this. So hom x y to x z. So I take any 2 maps like this, gf, so g from y to z and f from x to y, and I compose them, right? So I get gf. This composition map should be bilinear. Okay, so there's another sort of related notion. If you can also have like an R. If you have a ring R, you can have like an R linear category or whatever. In which case, you can give the Hom groups then an R module structure instead, and then the composition is R bilinear, R linear, or whatever. Cool, but I'm not going to talk about that. What else do we want for additive categories? So we need a 0 object. A has a zero object. So what is a zero object? It is an object that is both the terminal object in the category and the initial object in the category. So I should write that down. An object, usually, I mean, it's natural to just call it zero. That is both terminal and initial. Oops. And so because they're terminal and initial, we can put them together. For any two objects, x and y, we can create this zero morphism. So obtain zero map, which is just so we write this. So x to y, the zero morphism, which is just x goes to 0, goes to y. And there's only one like this, right? So cool. And then the last thing for additive categories is that the coproduct of any two elements exists. So finite coproducts exist. Objects. Okay, great. Good. And so, okay, in these additive categories, did I go too fast? Hopefully you can all see this. Good. You know, if you have any questions or anything to say, please, you know, interrupt me. I'm happy to stop and go back and anything. So, okay, in additive categories, we typically denote the coproduct by the symbol O plus instead of like this. Okay, so maybe I should say some more about this coproduct. So the coproduct in an additive category is also the finite product. So okay, we should see why. Okay, so if I have x and y, I want to form their coproduct, and it exists. So I write this thing down, x direct sum y. That also means I get two maps as well. I get I1, I2. These are going to be monomorphisms. Okay. You should think of like R modules, right? Your model for an additive category should be like abelian groups or R modules or something nice. Okay. So this is the diagram for the coproduct, and then there's this universal property, which many of you saw last week. Great. And now, what is the product supposed to do? So the product is like the other way around, right? So if I have x and y like this, the product is something that goes in here and two maps going out like this that satisfies some universal property with respect to this shape. And so, you know, I'm going to write P1 and P2 here, and it turns out indeed you can write xo plus y here. And okay, what is P1 and P2 here? P1 is actually going to be the map that you get if you take I1 and direct sum it with the zero morphism. Okay, so what do I mean by that? So we have to appeal to this universal property. And I don't want to spend so much time on this, but you know, one thing I can do is I can have something like this, something like this. I1, I can have 0 like this, and I can put x here. right? And so because the coproduct has this universal property, then you get this unique map this way. And this unique map is, this one is, where to write this? We denote it as I1 O plus 0. And this map is this one, right? And then you can do the same thing with P2, right? You flip 0 and I1, instead of X, you put Y. It's very similar. You can do it. Okay.
All right, I'm a little confused by what's the map from X to X is it supposed to be
Oh, it's
I1?
identity, or sorry, it should be, yeah. I might have messed that one up.
It's identity. So
Yeah, it should be id X. Yeah, thank you. Yeah, thank you. And then P2 similarly is 0 O plus id Y. Yeah, thank you. Okay, and you can check, there are some details to check that yes, this satisfies the properties, the universal property for a product. And okay, cool, good. Okay, so some things to note are, you have, if you compose the i's, which I'm just going to call inclusion, and the p's projection, if you compose them in certain ways, you get 0 or identity, depending on how you do it. So one thing is that, so I1, wait, no, I wrote this backwards. Inclusion followed by projection, at least, yeah, I1 followed by P1 is id X. And then again with I2, P2, that's id Y. Nice. And if you cross them, you get 0. 2 equals 0. Okay. And then one more that is a little bit more interesting is you get this one. You get, if you flip them and then add them together, so I1 P1 plus, so remember we're using the group structure in the hum sets. So I2 P2, this is actually going to be equal to the identity on the coproduct X O plus Y. Okay, why is this true? One thing you can do is you can do I1 P1 plus I2 P2 and precompose like I1. Okay, and then you're gonna just get, if you expand it out using the bilinearity of composition and the identities above, you will just get I1 again. But you should appeal to the uniqueness of these, of the inclusion maps coming from the coproduct. You should wave your wands, you say the magic word, and so then it turns out that this thing has to be the identity. Okay, but I don't want to get super categorical, but this is just fun. Okay, next. So we have a category with some extra properties. We would also like functors that sort of respect some of these properties. So I should introduce something called an additive functor, which admittedly today I'm not going to talk so much about, but it's possible in the future. We will need this language. So there's this thing called an additive functor. So a functor f from A to B, so both of these are additive categories, is additive if its action on the hum sets is actually also an abelian group homomorphism. So so when you look at the action on morphisms, so hum y to, so this is an A first, and then it goes to B. So fx fy if this map is an abelian group homomorphism. It's a homomorphism. Surprisingly, that's all you need. It turns out that you can show from this requirement, you can show that now F preserves coproducts. So now if I do F of X O plus Y, this will be isomorphic to, or I should say naturally isomorphic to, there's something to say here, but this is to, oops, how did I do that? To this coproduct for any two items, any two objects in A. And, you know, how do you show this? There are some details, but you essentially, you stare at these identities, apply F in a fun way, keep appealing to these universal properties. In fact, you know, a lot of what I saw when I was reading is like this direct sum. A lot of times they sort of soup up both the universal properties of the product and the coproduct together at once in some fun way. But okay, I will not worry about that. Okay, more language. So now we want to upgrade from additive category to abelian category. And one thing, I guess two things we need is we need to be able to take kernels and co-kernels, but okay, you can attempt to take kernels and co-kernels in additive categories in the following way. So I'll just draw the diagrams for kernel and co-kernel. And yeah, okay. So the kernel of a morphism in an additive category, so for say X to Y, call it F, is denoted kernel F. If, okay, this is, I'm saying if it exists, it is the limit of the following diagram. So I have X up here, I can map F to Y, and then there's also this zero morphism. Okay, this is one way you can do this. I mean, okay, so it's the limit of this diagram, right? So what I want is, you know, I'm going to put, if it exists, it's this thing, and these maps exist and they make the diagram commute, and it's universal with respect to this diagram, blah, 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 blah. Another thing you can do if you like, maybe you like equalizers more, maybe you like this instead. You can do this. The kernel is also the equalizer of this diagram. So again, yeah, okay, cool. And then there's also co-kernel. And there's a co in front, so you should imagine now it's like this dual thing. So co-kernel of this morphism F is the co-limit of, now I put Y in 0 here, and then X maps to Y with F, and then the zero morphism. And so, okay, then you get this. If it exists. And of course, you can draw a co-equalizer diagram. This will be what am I doing? No.
That's fine.
Put a Y there and then put the red.
Oh yes, yeah. What am I? Yeah. Yes. Yeah. Okay, great. Okay. So kernels and co-kernels in our modules, they're what you normally think of, but yeah, I've just introduced this language in case we need it. Cool. So important fact. In additive categories, monomorphisms are kernels and vice versa, and epimorphisms are co-kernels and vice versa. We are going to, I mean, I don't think I say we. I mean, this is a fact that gets used under the hood all the time. So I'll write this down. Additive categories. So monomorphisms are, okay, I said they are kernels. I should say monomorphisms are the kernels of something. So, and then likewise epimorphisms are co-kernels. Great. Okay, and then I should also define image and co-image. So the image of F is defined to be the kernel of the co-kernel. And then similarly, there's this co-image, which is the other way around. You take the co-kernel of the kernel of F. Now, okay, you probably have never seen this, and that's for a good reason. In our module, abelian groups, most things you've seen, they are the same. I myself have not actually seen up close. Maybe there's like a simple example out there, but I did not think of this.
Yeah, are you sure additive categories are enough to conclude that every monomorphism is a kernel, or does that need to be an addition?
Or maybe should this be abelian?
It certainly is true for abelian categories.
Okay. Okay, maybe I wrote this in the wrong order. Okay, we will see. Okay, when I get around to defining abelian categories, this will be true. Yeah, because surely, I mean, I said that one issue is that sometimes kernels and co-kernels don't even exist. So I don't even know why this would be reasonable in an additive category. My bad. So yeah. Okay. Yeah, so image and co-image. And so, okay, there's this diagram that you can draw involving the co-image and the image. So it's like this. So you start with kernel F. It includes into X. This is F from X to Y. And then, of course, there's co-kernel of F. So under X, you project down to the co-image of F. And then in Y, you stick in the image of F. We can show that there is a community. Okay, so this should, I suppose this should be in an abelian category. There exists a, okay, this is weird. Maybe my notes are out of order, but I think this should be in an abelian category. Or, okay. I've drawn the arrow in one way, but okay, fine. There exists a unique homomorphism S going from co-image to image. And this, I guess, should still hold in an additive category if all of these things exist. But the punchline is that in an abelian category, this S is actually an isomorphism. And I should write down properly what an abelian category is, which is just this last condition, more or less, on top of the other things I'm going to write down. Okay, so abelian categories. So an additive category is called an abelian category if now there are like two remaining things. So every morphism has a kernel and a co-kernel. And then the second thing is that for any morphism F, co-kernel, co-image, the thing I was mentioning earlier, co-image F to image F, this unique map S is an isomorphism. So in our modules, what this should look like is that if you actually calculate the co-image, you will just get, it will agree with image F. And then, okay, now it's like, okay, now indeed, all monomorphisms are kernels and all epimorphisms are co-kernels. And also, a morphism is an isomorphism if and only if it is a monomorphism and an epimorphism. So that is also good. And I guess from now on, I'm going to dispense with saying monomorphism and epimorphism, because from now on, I'm going to think about R modules if I can, or chain complexes of R modules. In which case, well, okay. It is easier to say injective and surjective. And so I'll use terms like subobject if it's a monomorphism. I'll use words like quotient if it's at the end of an epimorphism. So yeah. Okay. All right. How are we on time? 30 minutes. Okay, so one comment before I forget about abelian categories and just think R modules is, why there's always this interesting comment about why is it okay? Maybe am I forgetting something if am I missing something if I just stick to R modules? There's an interesting result that says that it's called the Freyd-Mitchell embedding theorem. It says that I'll write it down. If A is a small abelian category, then there exists a ring. Oops. A ring R and an exact. We'll talk about exact later. And then other adjectives are fully faithful, functor from A into R mod for this particular R. And so, okay, this A embeds as a full subcategory, blah, blah, blah. It's nice. So basically what it is saying is that, okay, if A is a small abelian category, it is basically in R mod for some particular R. Cool. And, oh, is there a question?
Does small mean not proper class? Or what's small mean for a category?
What does small mean? Small means small Hom sets, right? Or no, that's
Yes.
locally small.
Right, so small means there's a set of objects and between any two objects, a set of arrows, not a proper class.
Thank you, Mark.
Would that be restricted?
Would that be restrictive?
I mean, the category of abelian groups would not be a small abelian category, for example. Although obviously this theorem would still hold for abelian groups because it's already Z mod. But yeah, one other thing to note is that this R does not have to be commutative. So there may not exist any commutative such R.
Oh, right. Yeah, it could be a really messed up R, couldn't it? Huh. Yeah, I personally do not think too hard about these, but these are this does come up sometimes in some proofs, especially if you're just dealing with abelian categories proper, like yeah. So okay, we will just stick to R modules and sometimes even Z modules for some examples. Okay. Okay, so I mentioned this word exact earlier. Well, okay, that was for exact functor, but I want to talk about exactness as a general concept. This is like the maybe first or second thing that you see in homological algebra. So, okay, let's start with a sequence of maps between our modules. Maybe there are quite a few, but maybe I have just 3 modules at the beginning, like this. Let's say this one is F and this one is G. And so, okay, I call this a sequence, just because, well, okay, it's a sequence of maps going from left to right. I just stuck them together in this diagram. And I say this sequence is exact at B if the kernel of G is equal to the image of F. What should this look like in maybe an arbitrary abelian category? Maybe this should be naturally isomorphic, but okay. So, okay, in particular, what you notice from writing this kernel G equals image F is that if you compose the 2 maps together, GF is actually the 0 morphism. That is also true. And we say more generally that the sequence is exact, or call it an exact sequence, if at every node, at every module. So you just remove this at B if this is true at every module, if you have exactness at every spot in the sequence. So okay, exact sequence.
Sorry, what do you mean by a natural isomorphism between 2 objects?
Okay. Maybe canonical is a better word. Mark, how should this look in an abelian category? I'm actually not sure. Because now, if I'm just looking at an abelian category, kernel G and image F are just.
Yeah, so we can still talk about natural in the sense that it's, if you have like a morphism of chain complexes, then then kernel G becomes like a function. Yeah, so there is a meaning to say natural isomorphism, but there's a general fact about categories, which is that if you look at kernel G and image of F, they're both sub-objects of B, and sub-objects can only be isomorphic to each other in one way. That preserves the sub-object structure. So basically everything is fine. If we simply say they're the same sub-object of B, they can only be the same sub-object of B in one way.
Nice, thank you. Good. Yeah, so we say this is an exact sequence if it is exact at every module. Okay. So, okay, there's a particular kind of exact sequence that is very interesting. It comes up very often. It's called the short exact sequence. I will typically just write SES. And it looks like this. It starts with a 0 that goes to, so A, B, and C as usual, and then 0. I'll call this map F and this one G. And so, okay, some preliminary observations. Okay, what should I say? This, what am I? I've written this backwards. is a sequence of this shape that is exact. Yeah. And so because well, I'm going to say this short exact sequence is exact, there are a few observations. So F is injective. Why is this true? Well, okay, we need the kernel of F to be the image of this first red zero morphism. So kernel of F is equal to the kernel of this red zero map, which is equal to 0. Great, which is the trivial kernel characterization. So F is injective. Similarly, you can see that G is surjective. Great. Good. And so this is like, so we use these facts like freely, like it's yeah, very common in proofs. In fact, if we get to it today, we will do a diagram chase. That will be a lot of fun. We'll use these sorts of facts very, very commonly without even thinking about it, even. Okay. Okay. So now, instead of insisting that the kernel of a map on the left, or sorry, instead of insisting that the kernel of a map on the right is exactly agreeing with the image of the map on the left, we can loosen this and get something called a chain complex, where we merely only want containment, so that the composition of the two maps is still 0, of any two adjacent maps is 0. So, okay, a chain complex. So they look like this. They're typically written with suggestive lettering. So Cn plus 1, Cn, and this time I'll just write them in descending. There's also this chain, co-chain complex, but I'll come to that at the end, maybe. They're not that different. Cn minus 1, this was Dn plus 2 back here, and then this on the right is Dn minus 1, so on and so forth. And okay, only insist that the composite of any two adjacent maps is 0. That is to say, for any n, dn plus 1, oh dear, dn plus 1 is equal to 0. Yeah, good. Which is to say, so that the image of dn plus 1 is contained in the kernel of dn, right? So only containment. There are still, I mean, there's possibly some difference in the image and the kernel, and we want to measure that. Why would we measure that? Well, okay, maybe in topology, these sorts of complexes arise, and the difference in the image and the kernel measures some topological invariant. I'm not going to speak too much about this, but this is very useful for the topologist. And if you do cohomology, which is like the backwards version of this, you can rig it up in a certain way and get really fine invariance by making some kind of cohomology ring, blah, blah, blah. Really cool stuff, but not today. Okay. So maybe some terminology that I'm not gonna use today. Maybe tomorrow I will use this more. This terminology, I I think comes from topology. So I denote by Zn the kernel of Dn. And these are called the cycles. And then by Bn, I mean the image of Dn plus 1. And these are the boundaries. Okay, great. So there's this containment, right? So you have Bn, which is contained in Zn, right? Because the two Dn's, the two D's, they compose to 0. Oh, D for differential. This notation, this name probably also comes from topology as well. At least, there's this derived cohomology where it's this, it is a differential in some way. Yeah. Okay, so Bn is contained in Zn, and Zn, so it's the kernel of Dn, means it's contained in Cn. So nice notation. And so now the thing we've been waiting for is homology. So what is homology? It's denoted by Hn, so subscript, which is Zn modulo Bn. The cycles mod the boundaries. So I don't actually think, in my head, I don't think Zn mod Bn. I always think kernel mod image. So if you like, I'll write this down. Yeah. Nice. Okay, so maybe, okay. It is 45. I've got like 15 minutes. Maybe we don't do that example. I want to continue with chain complexes. So we have these chain complexes of R modules. It is the case that they actually form a category in their own right. But what do I mean by that? I should specify the morphisms of chain complexes, right? So the objects, of course, are the chain complexes, but what is a morphism of a chain complex? So, and the name of, so typically denoted like CH R mod for chain complexes. R modules. And so, okay. Maybe you would like a notation to refer to a chain complex succinctly. You don't want to have to write down this whole thing every time. Just call it C bullet. That's nice. Maybe I've already used this notation already, but yeah, I will use this here. So a morphism F of chain complexes C and D is really a collection of maps Fn. Each one, so each Fn goes from Cn to Dn, but they're not just the maps. They have to play nice with the differentials in a certain way, such that so if you actually drew the map out all the way, so like this, so Cn plus 1, Cn minus 1, dot, 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 and then the one down here for D. Oops. So Dn plus 1, Dn minus 1. So this map here is Fn plus 1, this one here is Fn, this one here is Fn minus 1. What I mean by plays nice is that each of these squares, they commute. And so to write this, down, in other words, is for all n, we want, how should it look like? We want dn fn to agree with fn minus 1 dn, right? Yeah. So what does this actually buy us? Anytime we have a morphism of a chain complex, they actually preserve the cycles and the boundaries. What I mean by that is that, like, okay, okay, I should write this down carefully. Morphisms of chain complexes preserve cycles and boundaries. That is to say, if say Z is in Zn, right? And you can, the notation is usually like you can specify C bullet, right? It's the cycles of the n cycles of the chain complex consisting of the C modules, then Fnz belongs to Zn d bullet. And then similar statement for the boundaries. And so, okay, then what you can do is, because the cycles and the boundaries are preserved, morphism of chain complex actually induces a morphism of the homology. Get this induced map on homology modules. Homology. Oops. Goodness. Hn to Hn. Induced by F, which is cool. And so, continuing this line of thought, maybe another good way to say this is that each Hn defines a functor from chain complexes to R modules. So each Hn determines a functor from CH mod to R mod. Nice. And the chain complexes are actually quite a nice category. They actually form an abelian category. So what should I say? You should check a few things, right? Like maybe I'll just say these things out loud. Chain complexes form an abelian category. So I mean, if you look at additivity, you can add the chain maps degree-wise. So if you have two chain maps, F and G, you add them degree-wise. So the nth map in the sum is the sum of the nth maps, blah, blah, blah. The zero object is the zero complex of zero maps and zero modules. You take the product and the co-product, also degree-wise. And then, okay, so that's additivity, how to do kernels and co-kernels. You can do, in general, you want to talk about sub-objects and quotients of chain complexes. Again, you define them degree-wise, but you need to also check that, like, the maps that you get. So if you have a sub-object and you define a sub-object degree-wise, so if A is a sub-object of B, then in the chain complex it'll look like this. So an plus 1, an minus 1, blah, 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 so on and so forth. You'll get for each point 1 bn minus 1. You'll get these inclusion maps, but you need to also check that they are actually morphisms in the category, so they also need to make these squares commute. Oops. So, and then the same for the quotients on the other side. And so, okay, then you can check that, okay, maybe I could define a kernel by doing the kernels component-wise or the co-kernels component-wise. And, there are a lot of details to check, but it all works. And yeah. And then, you might worry, you might ask, like, oh, what does exactness mean in the category of chain complexes. And so you can actually show that if you have a short exact sequence of chain complexes, so if I have 0, A bullet, B bullet, C bullet to 0, or if I just have I just have a sequence like this. This thing is exact. That is a short exact sequence. If and only if each degree, in each degree, it's a short exact sequence. Which is cool. I mean, you can try all these things. They're good, fun exercises. Okay, but I've mentioned this short exact sequence of chain complex. Why would we ever care about this? I got like 5 minutes. So, okay, unfortunately, no diagram chase. Maybe I'll just mention the snake lemma. I mean, I'll be here if people want to see me diagram chase, like, we can do it, but like, so if I have a short exact sequence of chain complexes, so 0, A bullet, B bullet, C bullet, and then 0, there's this neat device that I can get from it. It's called the long exact sequence in homology. And I mean, when I write this down, it might feel sort of weird. Like, I mean, why would I ever get this? I think maybe the motivations are more applicable, or maybe it's easier to see that this thing should happen in topology in some way. But at least on the nose, it looks a little odd. So it looks like this. So why do I call it a long exact sequence? It's because it goes on in both ways for a while. At least at one spot, it could be 0 depending on the indices. Okay, whatever, blah blah blah. But in principle, it could go on in both directions for a while. So maybe I'll label the chain maps here F and G, or the morphisms of chain complexes F and G. So dot dot dot. Remember that I said that the chain maps induce maps on homologies, and these are the ones. So I have G here, the induced map G going to Hn plus 1 and C bullet. And then there's this weird map delta that I'll talk about later. It is a homomorphism, but it's not the ones that come from the data of F and G like directly. You have to construct it in some funny way. Then there's Hn A bullet, the map induced by F, Hn B bullet, and then the map induced by G, Hn C bullet, and then again this weird map, and then Hn minus 1 A, so on and so forth. And so, okay, maybe if you've done some algebraic topology before, this is pretty nice because, if you know something about most of the terms in this sequence, you can always leverage this exactness to sort of either restrict or even completely determine some facts about the other modules that you don't know about, like the rank or isomorphism class, blah, blah, blah. You can figure out all these nice things. So it's a useful device. We'd like to have these sorts of things. And it also basically tells us how they fit together, right? It's good. Now, how did you get something like this? In particular, how do you get these delta maps? It's sort of an involved process, but more or less it boils down to something called the snake lemma, which is what I wanted to do the diagram chase for. So I'll just write down the snake lemma and maybe I'll call the official lecture. The rest of this was just going to be doing the snake lemma or parts of it. I mean, even the snake lemma is like very tedious to prove because you have to sit down and check every detail, right? There are a lot of things, but I'll write down the snake lemma. So the snake lemma is one of many results in a zoo of like diagram chasing results, where you look at the diagram, they give you a few pieces, and somehow you determine new facts about something related or something in the diagram. You produce maps out of thin air, something like that. They're very interesting, but they often involve a lot of details. So the snake lemma is as followed. So in a commuting diagram, that looks like the following. So if I write A prime, B prime, C prime, and 0 here, then I have maps going down like this. A, oops, B, C, maps going this way, and then another 0 here. If in this diagram, the rows are exact, then there is a sequence, there is an exact sequence as follows. It looks like this. Okay, so I should label the maps some more. So this one is F, this one is G, this one is H. Let's say, and then it starts from kernel F to kernel of G, then kernel H. So far, I mean, this is okay. But then there's this weird delta map here that we need to talk about. And there's co-kernel of F, co-kernel G, co-kernel H. Right. So this forms an exact sequence, and there's some other facts as well, like if you can prepend and append 0 here, then you can also do the same thing here. But okay. What is this delta map? This delta map is really weird. This delta map is defined by, okay, if I write, say, P and I here, I say P and I because I've assumed the rows are exact, right? So P is suggestive for projection, I is suggestive for inclusion. This delta is going to be, I start with the right inverse of P. Okay, well, really, I start with including the kernel of F into, or sorry, kernel of H into C prime. But then you do the right inverse of P, then you do G, and then you do the left inverse of I. You can actually show that what you get after applying G is actually already in A, but I mean that's part of the proof. It's this really weird map. And so, okay, why does it look like this? Maybe I write down what the actual snake is. And luckily I'm on a tablet, so I can just copy paste this picture. Why is it called the snake lemma? So I put cur F up here, cur G here, cur H here, and then the co-kernels here. Co-cur G, co-cur H. The snake is this. That's this delta, and that's why it's called the snake lemma. But okay. This is a good exercise. I'm happy to work out parts of it right now if you like, but it is the hour. So officially this lecture is ended, and I think I will stop recording as well. And then we can how to do this. I've got to do something. Can I stop recording?
I have a question, Sai.
Stop.
Sai?